In this video, I'm going to talk about continuity equation in semiconductors. In general, continuity equation is a very fundamental concept where you would find this continuity equation in various fields, for example, like fluid mechanics, electromagnetics, thermodynamics, and even in semiconductors. All of them, in terms of equations, might look different, but all are related with a single concept. And the concept is conservation of some quantity. So in electromagnetics, it talks about the conservation of energy, which tells energy is neither created nor destroyed. Whereas in semiconductors, it talks about conservation of charge, where it says charge is neither created nor destroyed. In specific, we will derive single variable continuity equation in this video. Let me take a semiconductor material where we are measuring distance in this axis, and let me take the cross-sectional area of this semiconductor is A. Let me take an infinitesimal slice of this semiconductor material where its cross-sectional area is same as the area we considered A. And let's say this value is x and this value is x plus del x, which means the thickness of this small box is del x, and we can say the volume of this box is A times del x. Let's say the number of electrons in this box of volume A del x is increasing, so we can represent that in mathematical form as del n over del t times A times del x, because n units is number of electrons per centimeter cube, which is electron concentration, changing with respect to time. But we are talking about total number of electrons increasing with respect to time in this box. That's why we multiplied this with A times del x, so that the units of this would be number of electrons increasing with respect to time in box. So this increase of electrons with respect to time in this box should be equal to, let's say at x, the current density that is flowing in is J of x. And of course, we are talking about electrons, so we should call this Jn of x. And let's say the current density that is flowing out is Jn of x plus del x. The number of electrons in this box can increase only if Jn of x is higher than Jn of x plus del x. So let me represent that. So Jn of x, the units of this is number of electrons flowing per unit time per unit area. But we are talking about number of electrons per unit time. So that's why we need to multiply this with area A, the cross-sectional area. And this basically tells us the amount of charge flowing. So we need to divide this with the charge of electron, which is minus q, minus the outflowing current density, which is J of x plus del x. And as we are talking about number of electrons, so we should be multiplying this with the area of cross section divided by minus q, because the charge of electron is minus q. Now this basically tells us the number of electrons flowing in to the box, and this basically tells us number of electrons flowing out of the box. If the number of electrons flowing into the box is greater than the number of electrons flowing out of the box, we can say the number of electrons in this box would increase. That's what it says. Now, is there any other reason why the electrons in this box would increase? Now, we have discussed a topic called generation and recombination, which means the carriers in this box can actually increase if the generation of electrons is greater than the recombination. So I'm going to write this here. Let's say the generation of electrons is given by Gn. We know that Gn basically talks about number of electrons generated per unit volume. But we are talking about number of electrons in this volume. So we should be multiplying this with A times del x minus the recombination rate, which is Rn times A times del x. Now we have this where this can be said as number of electrons generated in the box. And this recombination basically tells number of electrons recombined in the box. If the generation of electrons is greater than the recombination of electrons, then we can have the electron number increase in this box. So to summarize, we can say the number of electrons with respect to time can increase in this box if the inflow of electrons is greater than the outflow of electrons, and if the generation of electrons in this box is greater than the recombination of electrons in this box. To understand this better, let me take an analogy where we have, let's say, a lake in which we have water. How can the water content in this lake increase? It can increase if the inflow into this lake is greater than the outflow to the lake, which means the inflowing water is greater than the outflowing water. So the water in this lake increases, which is similar to the electron flow into the box is greater than the electron flow out of the box. And similarly, we have a situation where, let's say, we have sun, which evaporates the water, which means the content of water would decrease in the lake. But at the same time, we can have clouds, which basically can produce rain, which will fill this lake. We can say total, the water content in this lake can increase if the inflow is greater than the outflow, and the rain contribution of water is greater than the evaporation of the water. Rain and evaporation can be actually attributed to the generation and recombination of carriers in this box. Now let me rearrange this equation to make it smaller, where I can write del n over del t is equal to, I'm taking a del x, which is common in all of them, cancelling out a del x, and I'll have del x here. So that we can write this as 1 over q times j n of x plus del x minus j n of x divided by del x plus Gn minus Rn. Now in fact, we have just represented the current density in terms of just space, but of course it will be depending on time as well. So let me add time function here. Let me assume this in small box where del x is tending to 0, so that we are talking about infinitesimal box. So let me apply the limit del x tends to 0 on both sides, so that I can write this del n over del t can be written as 1 over q times. This looks like a standard differential equation definition, and that too, this is a partial differentiation definition. So we can write this as a del Jn over del x, the spatial variation of current density, plus Gn minus Rn. So this is the continuity equation, which talks about if the carriers in this box increase, they increase only because there is a difference in inflow and outflow, and there is a difference in generation compared to recombination. And of course, this del n by del t can be negative as well. When it is negative, which means the electron concentration in this box is decreasing, and that is attributed to the fact that the inflow and outflow difference and the generation and recombination difference. And it actually talks about the conservation of charge, that the charge is neither created nor destroyed. It is transferred from one place to another place. Similarly, we can write for holes as well, the continuity equation for holes, where del p over del t is equal to minus 1 over q, because in this equation we took electron charge as minus q. If you take plus q and if you substitute wherever we have n with p, we would get hole's continuity equation. So that's why we are having here minus times del jp by del x plus gp minus rp. And these are the continuity equations for electrons and holes. And if you look at here, it's a single variable continuity equation. What I meant by this is, we are assuming that there is a variation with respect to x. At a given x, whatever is the value of J and electron concentration or hole concentration, they're basically exactly same as we go in y direction and z direction. So that's why we simplified this and did only a single variable assumption. Now, of course, this equation doesn't tell everything, in the sense that Jn, if you see, is given by Jn drift plus Jn diffusion. And this equation is given by Q times N times mu N times E plus Q times dN times del N over del X. Now, in place of Jn, we are supposed to substitute this expression so that we get the expanded big continuity equation in single variable. And similarly, we can write for Jp, which is given by this equation. For completeness sake, let me write the entire equation for electrons and holes by substituting this Jn and Jp. So once we substitute the current density Jn into this equation, this is how it looks. And similarly, for whole continuity equation, if you substitute the expression for Jp, this is how the complete expression looks. So basically, continuity equation in semiconductors represent the conservation of charge, which means charge is neither created nor destroyed.